I want to begin with an interesting question that Bajaya just brought up before the class, which has to do with this notation with Ks and subscripts. So this is not a regular tensor notation. Okay, so K is not a regular tensor that has components in X, Y, and Z. Okay? The point is just that we have these liquid crystal distortion modes, the splay and twist and bend. And each of them has some coefficient, right? So there's a coefficient of splay squared or twist squared or bend squared or delta squared. And these coefficients have conventional names, which have come down for many years, okay? And there are actually two different conventions for the names, right? And so I should have mentioned that in the last class. Right? There is one kind of convention where people refer to K11, K22, K33, and then there's a shorter convention where people just say K1, K2, K3, just like that, with one subscript instead of two subscripts. I don't really know the history of where these conventions come from. But the point that I should emphasize is that these are not tensors, right? This is not like a Q tensor, say, that has components Qij, where the I and the J represent X or Y or Z. So this is a different sort of thing. These are just labels for different elastic coefficients. Right? And so there's no rotation of coordinate systems that changes K11 into K22 or anything like that. Right? These are not components of a tensor. These are just different coefficients. And so you should not make up a tensor notation where you write something like Kij, Nij, anything like that, right? This is really wrong, okay? Because the subscripts on the Ks are totally different from the subscripts on the Ns or the Qs, right? The subscripts on the Ns and the Qs and any kind of tensor, right? Those are subscripts that have to do with direction in X or Y or Z. The subscripts on the Ks are nothing like that. They are just labels. And so, it would be even better to say, K sub splay. That would be a nice label, wouldn't it? Right? We could say K sub splay, or even just to be short, how about K sub S, K sub T, K sub B, K sub delta, right? If I were making up the notation from scratch by myself, I would use labels like this, okay? And I wouldn't use labels like K1 or K11. However, I'm not starting from scratch. People have been doing liquid crystal science for many decades. And so we need to stick with these labels, right? So that we can communicate with other liquid crystal scientists, okay? But as we stick with the labels, we recognize that they have nothing to do with tensor subscripts, as I've been showing you, right? And so, for other things like K12, it's not as if there's something like that, but it's very small, right? There's just no such thing, right? All right. End of sermon about that. Okay, so in the class last time, I showed you my own personal notation that I love so much for how to write out the Frank free energy in terms of these four modes: splay, twist, bend, and delta. And then I also showed you the standard form written in terms of splay, twist, and bend. And then this other saddle splay term, which is usually a constant. And so it's usually not something that we need to consider explicitly.
Jonathan, I just sent you one formula by email.
You sent me a formula by email.
Yes.
Okay. What's in that formula?
That is looks like tensor form.
Okay, I have to open my email program because I closed it when I was trying
Okay.
to get my
Because Tony used that formula in the first semester, and so where
Oh
K
no, am
can
I
be
really
written in a tensor
disagreeing
form.
with him? Uh-oh, bummer. Okay, let's see what you sent me. Okay, here, I see email from you. Um,
And so
it's
when
loading.
during the seminars, maybe one semester, I think 2 semester ago, and when I asked with other professor, and he told me that K24 is enough to consider, but we don't need to consider we don't need to consider other term of elastic constant.
Um,
During the
this is
simulation, we
this
mostly
is an
use only three
interesting
constants.
equation, but Jaya, I'm going to need more context. And
Okay.
so maybe if you send me the whole reference or something, then I'll be able to see the context and I can give you a better
Yeah,
response.
okay, because Tony used that equation in lecture, but I mean, sir, but there is no any reference how he used that.
Uh, we'll have to talk about it separately.
Okay, okay, thank you.
Um, there's a lot of terms there, and I don't know what it all means. But thank you. We'll talk about it separately. What I want to do in this class is to give an example of how to work with the Frank free energy. Right? And so the kind of problem that I want to consider uh, is a problem where we want to find the director field. Okay, so our goal is to find the director as a function of X, Y, and Z, right? That's a common goal in liquid crystal physics, is that there are multiple competing influences on the liquid crystal. Maybe there's a boundary condition that wants to do one thing, and an electric or a magnetic field that tries to make the liquid crystal do something else. And in response to these complicated competing influences, we get the best possible compromise. And so we want to find the function n of x, y, and z to minimize the free energy. The example that I want to show you today is the Frederiks transition. This is a standard example in liquid crystal physics. It's a very a common sort of situation where you have the combination of boundary conditions and elasticity versus an applied electric or magnetic field. And so the point is that the boundary conditions and elasticity favor one sort of director field. The applied electric or magnetic field favors a different configuration of the director. So these two things are fighting against each other, and we want to get the best possible compromise to minimize the free energy. Okay, so let me show you a few different versions of this. I have like 2 or 3 versions of this to show you in this class. Okay, so here is version number 1. Okay, this version number 1, so this is in a semi-infinite system. Okay, so you remember we had the word semi-infinite system earlier in the semester, right? What this means is a system that has a wall on one side, but it goes off to infinity in the other side. Okay, so it's bounded on one side, but it's infinite on the other side. Okay, so here in this picture, let's say we have a wall at x equals 0, okay? But it goes off to infinity as x goes to plus infinity, okay? So it's semi-infinite in x, okay? So we could say x goes from 0 to infinity. And then let's suppose nothing depends on y and z. We'll just make up a geometry that says it's independent of y and z. Okay, now suppose that the wall is designed so that it strongly anchors the director. All right? So it anchors the director so that n has to be in the z direction at x equals 0. Now, your other more experimentally oriented classes will teach you things about how to make a wall that does this kind of effect. For example, there are methods to rub the wall in the z direction, and then the microscopic scratch marks from rubbing the wall can tend to align the director in the z direction. Okay. So let's suppose that has been done, okay? So that the director tends to point in the z direction at x equals 0. And in fact, I'll say it strongly anchors the director at n equals z when x equals 0. Okay, so the director has to be pointing in that direction. Okay, so that's what's illustrated by this little cylinder, right? The cylinder represents the director, and here you can say it's in the z direction at x equals 0. Now, what about in the bulk? Okay, so the bulk means the interior of the sample, the infinite region that's away from the wall. Okay, so in the bulk that is away from the wall, we have a magnetic field, H. And the magnetic field is here in the y direction. Okay, so that's what's uh, illustrated by this arrow for H down there. Okay, it's in the Y direction. So that means, let's say the liquid crystal has some positive magnetic anisotropy, so it tends to align with the magnetic field. Is this a subject that you've already covered in classes, say from Professor Yockley or anyone else? Yes, okay. All right. Have you already done exactly this problem with Professor Yockley? No. All right. So we'll say if there is positive magnetic anisotropy, so N aligns with H. Or really, I should say N aligns with plus or minus H, because N is a two-headed vector or a no-headed vector, right? So it could be pointing either parallel or, whoops, it could be pointing either parallel or anti-parallel to H. Those two would be equivalent states. Okay, so that means that in this kind of geometry, there's a conflict between the wall and the magnetic field, right? So the wall tends to align the liquid crystal in the Z direction over here, and then the elastic free energy says, well, if the crystal is aligned in the Z direction here, it should stay aligned with the Z direction everywhere going into the interior. Okay? By comparison, the magnetic field says the liquid crystal should be pointing in the Y direction, this way. Okay? So these two things are fighting against each other. Okay? So presumably the director will do something that's kind of a compromise so that it'll point in the Z direction right at the wall, and then it'll twist over like this, and it'll point in the Y direction in the interior. Right? And so we want to say, well, what is the director as a function of the X coordinate as we're going outwards from the wall? Okay. So is the question clear, if not the answer? Okay. Yes, you're good with that? Okay. So one way to deal with this is we can start by assuming that the director is everywhere in the YZ plane, right? That is, the director over here is in the Y direction. Over here, it's in the Z direction. In between, probably rotates between Y and Z like this. But there's no reason for it to point in the X direction. That would just make extra derivatives of the director, which would have no benefit. Okay, so let's then do a calculation where we assume N is in the YZ plane. So that means that we can write it explicitly in terms of some angle in the YZ plane. So we could write it as N is 0 in the X direction, comma, sine theta in the Y direction, and cosine theta in the Z direction, where theta is the angle away from the Z axis. Okay, so in a picture like this, right? So here, theta is equal to 0, right? And here, theta is 90 degrees. So the theta is dependent on the coordinate x. So this is the director n as a function of x. Okay, so 0 sine theta of x, cosine theta of x. Okay. Now, let's figure out what is the Frank elastic free energy for this kind of variation. So we have these three terms in the Frank free energy in the standard form of the Frank free energy. I'll do things with the standard form. One good reason why I could do things with the standard form is that the boundaries are fixed, right? We have a fixed director over here and a fixed director at infinity. So the saddle splay thing is fixed. So I'll do everything in the standard form. Okay, so the splay, that is the divergence of n. So that is dx and x plus dy and y plus dz and z. Oh, well, nx is 0, so that's 0. And nothing depends on y or z. These terms are all 0. Good news, the splay is 0. Okay. How about the twist and the bend? Well, they both involve the curl of n. Okay, so the curl of n, let's see, that's dy and z minus dz and y, and dz and x minus dx and z, and dx and y minus dy and x. Okay. Most of these things are 0 because nothing depends on y or z. Okay, so the only non-zero terms, let's see, there's a term which is negative x derivative of nz. So that is sine theta times dx of theta. Okay. And then there's a term that's dx of ny. So that is cosine theta dx of theta, like that. Okay, so let's see what's the twist. So the twist is n dot del cross n. So that's 0 times 0, right? Plus sine theta times sine theta d theta dx. So that's sine squared theta dx of theta. Plus the z component times the z component. So that's cosine squared theta d x of theta, right? So it's d theta dx. What about the bend? Well, that's n cross del cross n. Okay, so, oh man, do I have to do this? Okay, it's the y component, so sine theta, times the z component, cos theta dx theta, minus the z component, cos theta, times the y component, sine theta dx theta. Oh, well, that's 0. Haha, good. Okay, what about in the y place? It's the z component cos theta times the x component, 0, minus the x component, 0, times, well, whatever. It's 0, okay? And this is an x component, 0 times something, minus the y component, sine theta, times an x component of 0. Ah, the whole thing is 0. Good news. Okay, so that means that the standard form for the Frank free energy, that's the elastic free energy, that is an integral over all volume of 1/2 K22 times the twist squared. Okay. So that is an integral over all the volume of 1/2 K22 d theta dx squared. Now for this integral, nothing depends on y or z. So I can just factor out the area in the yz plane. And then there's an integral over all values of x. So an integral over x from 0 to infinity of 1/2 K22 d theta dx squared. Okay, you guys good with that? Now, there is also a magnetic free energy, which says, how does the liquid crystal align with the magnetic field? Okay. This is something which we haven't really talked about in this class. Perhaps you guys have gotten that from Professor Yockley in a separate class. Okay. But in general, the expression for that is an integral over volume of something times the magnetic field dotted with the director squared. And so it has to be squared because we know that the director is equivalent to negative the director. And so the free energy has to be independent of whether we put in plus n or minus n, right? Those two things have to be degenerate. So it must be an even function of the director. So h dot n quantity squared is the simplest thing that's allowed by symmetry. The coefficient of this is conventionally written as -1/2 delta chi over mu naught, where delta chi is the magnetic anisotropy. And that determines whether the liquid crystal director tends to align parallel or perpendicular to the magnetic field. Okay? So delta chi positive means it favors parallel alignment, and delta chi negative favors perpendicular alignment. And mu naught is a fundamental magnetic constant, whatever that's called, permeability of free space. There are other derivations of this based on fundamental magnetism, which you may have seen in other courses. That's fine. Okay, so let's use this form. Okay, so we know that the magnetic field, that's something in the y direction, right? That's how I designed the problem to begin with, right? Is that the field is
Jonathan, I have one general question.
please.
Okay, so normally we calculated similar for electric field in Philip Bosch course, but I would like to know, we have two kind of anisotropy. One is anisotropy in dielectric constant, and other is anisotropy in magnetic susceptibility. So liquid crystal always have these two kind of dielectric anisotropy, or sometimes it's possible to have only dielectric anisotropy in dielectric constant, but no any dielectric anisotropy in magnetic susceptibility.
Liquid crystals will always have both.
Okay, good.
Anisotropy in both the coupling with an electric field and the coupling with a magnetic field. Usually the electric effect is bigger and the magnetic effect is
But there is no any relationship between the magnetic. I mean, there is no any relationship between dielectric anisotropy in magnetic susceptibility and dielectric anisotropy in dielectric constant. Then how is possible? In case of dielectric anisotropy, it will comes due to the different. I mean, different. Maybe it will comes from permanent dipole moment. It might be possible in case of anisotropy in dielectric constant.
Yeah. These things don't come from a permanent moment. They come from a material that is polarizable, right? That is, you can induce a dipole moment. So if you apply a magnetic field, you induce a magnetic moment, and then the applied magnetic field couples with the induced moment. Or if you apply an electric field and you induce some electric dipole moment, then those two things couple. Right? That's another way of seeing what's the quadratic effect as opposed to a linear effect, right? So I don't know of a mathematical relationship between those parameters, but well, I don't know. But let's go with this story here and just say what happens, assuming there is some such coupling. Okay? And then if you put on a magnetic field, you have a field in this direction, and the director, as we set it up already, that's 0, comma, sine theta, comma, cosine theta. Okay, so the dot product of those things is h sine theta. So that means that the magnetic free energy is this integral of minus a half delta chi times h squared over mu naught times sine squared of theta. Okay. And this integral, we could even say, well, nothing depends on y or z, so we'll just factor out those lengths. And then we have an integral from 0 to infinity of minus a half delta chi h squared over mu naught sine squared theta. Okay, so now we have two terms in the free energy. Okay, so the total free energy, combining those two things, that is well, the area factors, then an integral for x from 0 to infinity, and there is the elastic term, a half k22 d theta dx squared, and then the magnetic term. So a half delta chi over delta chi times h squared over mu naught sine squared of theta of x. Okay, so this is an integral for the free energy. All right. We want to minimize it over all functions theta of x, okay, with the boundary condition that theta of 0 has to be 0, so that the director will be aligned in the z direction at x equals 0. Okay. So this is a standard sort of problem in liquid crystal physics. Okay. So let's see how to solve it. Okay. So it is, of course, a problem of variational calculus. So we can solve it using the same methods of variational calculus that we talked about earlier in the semester. That is, we want to calculate this functional derivative of theta with, of the free energy with respect to theta of x and set that equal to 0. So we can do that using the same techniques that I've shown you earlier in the semester. Okay? That is, there's a factor of y, lz in front of everything. Okay? Now we want to get the functional derivative of the first term. That is a first derivative squared kind of term. We know how to do that. We do that by the integration by parts trick that I showed you earlier in the semester. Right? What you get from doing that trick is just like in the bobsled race or anything else, right? That you get a negative sign that comes from the integration by parts. You get a factor of 2 that cancels this 1/2. You have the coefficient k22, and then a second derivative, d2 theta dx squared. Okay. So this will be hopefully familiar from the problems that we did before, but if it's not, we can talk about it again.
But I think, I mean, in anchoring, normally we use sine or cosine potentials, and I think idea is similar or different, because in Oleg's some course.
Here, instead of that, I have a strong anchoring. Theta of 0 has to be 0. So it's not that there's some energy associated with the anchoring. The anchoring is infinitely strong. So it's like what you're describing with the anchoring energy times infinity, right? And so the anchoring is locked in at theta equals 0. So this is the term that comes from differentiating the first piece. Okay. Then we need to differentiate the second piece. That's not a derivative term, so we can differentiate it in the regular way. Okay, and we get minus a half delta chi h squared over mu naught. And the derivative of sine squared is 2 sine theta cosine theta, like that. So this all has to be equal to 0. Again, these factors cancel very conveniently. Okay, so our differential equation then simplifies to this nice form of k2 2 times the second derivative of theta with respect to x plus delta chi h squared over mu naught sine theta cosine theta equals 0. So that's a differential equation that we want to solve. Okay, this is the Euler-Lagrange equation for this problem. A standard way to simplify this is to divide through by the coefficient k22, and then we would get the equation in the form of the second derivative of theta is negative something, negative delta chi h squared over mu naught k22 sine theta cosine theta. Now, this coefficient, this combination of factors, better have dimensions of 1 over length squared. Right? You can tell that because theta is dimensionless, and here's a length squared in the denominator. Right? This stuff is dimensionless, so this better be 1 over length squared. So we can call this as 1 over xi squared, where xi is equal to 1 over the square root of this thing. So 1 over h times the square root of mu naught k22 over delta chi. Okay, so our differential equation d2 theta dx squared is minus 1 over xi squared sine theta cosine theta. This is a nonlinear differential equation, so it's a little bit of a pain to solve it, but there is an exact solution, which I will just show you. Okay. The exact solution is like this, that theta of x is plus or minus inverse sine of the hyperbolic tangent of x over xi. Okay. So this is a solution. It's hard to derive, but it's not hard to take this and plug it into the differential equation and verify that it works. Okay. The mathematical form is what's shown in this plot. So in this plot, you can see the wall is here at x equals 0. So here at the wall, we have a a director with theta equals 0. So the director is pointing in the z direction. And then as you go into the interior, the director is twisting. It changes from an orientation of 0 up to pi over 2. Or it could twist in the other way. It could go down to negative pi over 2. So it is free to twist in either direction, but in either case, you see this kind of a variation, okay? So that near the wall, it's aligned in the way that the wall requires. And away from the wall, it's aligned in the way that the magnetic field favors. And in between, there's some transition region. Right? So there's a region in between, something like this big, where the director is gradually changing from being in the wall direction to being in the bulk direction. You could define the transition region to be this big, or maybe you would define it to be that big. It doesn't really matter, right? The point is that the characteristic scale of the transition region is given by this length psi, okay? So psi is the length scale of that transition region, and it gets the name of the magnetic coherence length. And you remember the equation that we came up with for psi is like this, that it has a magnetic field in the denominator and K22 mu naught over delta chi inside the square root. Okay, so let's try to interpret the dependence on these different parameters. Okay, the magnetic field is in the denominator. That means if the magnetic field is really small, then the director will stay in the way favored by the wall for a really long length scale. Maybe it'll go up to pi over 2 eventually, but it could take a huge distance before it gets up to pi over 2. Right? So if there's a weak field, then there's a large region controlled by the wall, like this or like that. On the other hand, if H is really strong, then there's a short distance controlled by the wall and a long distance controlled by the magnetic field. So if H is really strong, you get something really abrupt like that, or like that. You could also see what's the effect of the elastic constant K22, right? If K22 is really big, then derivatives of theta are really expensive in terms of energy, right? It takes a lot of energy to vary theta, okay? So if K22 is really big, then theta will change really slowly, like this, right? On the other hand, if K22 is really small, then hey, no problem, theta can change quickly, something like that. Okay, so that's the kind of thing that you should be thinking about when you see an equation like this one. This is the situation for the semi-infinite problem. Okay, so that is for a problem like this one. Okay, so that's what I wanted to show you for this example. For the, how am I doing on time? Oh no, Okay, I got to talk for another 10 minutes or so to do another example. If you have to go, that's fine. You can watch the recording. Okay, now let's think of another example where you might have a finite system. So here is a new variation on the problem. Okay, so this is a finite system that has two walls. Okay, so here's wall number one, and here on the other side of the cell is wall number two. And now both of these walls require the director to be in the z direction. Okay? So these walls are both rubbed in parallel ways. Okay, so this wall requires n in the z direction at x equals 0. And this wall requires n in the z direction at x equals, what did I call it? D. Okay, so it's a cell with some thickness D between the walls. Okay, so both of the walls require the director to be in the z direction. Maybe the director will just be in the z direction everywhere. That would be a nice, simple configuration. But let's suppose in between the walls, there's a magnetic field, which is again pointing in the y direction. So in between, maybe the director will tip over in the y direction, like I drew in this picture. Okay, and then it'll go back, right? So in this picture, we have the director that's in Z, and then it tips over to point sort of in the Y direction, and then it straightens up again and goes back to the Z direction. That could happen too. So what would we guess for the solution? Okay, here, I'll write down a guess. Whoops. Let's make a guess. So my guess will be a plot for theta as a function of x. Okay, for x going from x equals 0 to over here, x equals d. These are the two walls. If the two walls are very far apart, then we could say, well, near one wall, it's like a semi-infinite system. It could be something like that. Near the other wall, it's also like a semi-infinite system. So it'll be something like that. And in between, they'll just join up. Okay, that should work fine as long as the wall spacing is much bigger than psi. If d is much greater than psi, we'd get something like this. Okay. Okay. Well, what if d is not much greater than psi? What if d and psi are sort of similar? Okay. Well, in that case, it's more complicated, right? In that case, if d and psi are similar, maybe d is smaller or psi is bigger. Okay, then if this is x equals 0, this is x equals d, maybe it starts to go up over here. Maybe it starts to go up over here, but it can't get all the way to pi over 2 because there's just not enough room. So it goes up a little bit and then it comes back down. So this could be another possibility. Or maybe it just wouldn't go up at all, right? Maybe for a different plot, this is theta of x. And then here's another one, theta of x, if x equals 0, and here's x equals d. Maybe it'll just stay right there, okay, and not tip over at all. That could happen too. One way to solve this problem is numerically, right? That is, we want to solve the differential equation, right? We still have the same differential equation. We still have this equation, okay? So I'll say, let's solve the same differential equation. Sine theta, cosine theta. But now there are two boundary conditions. That theta at 0 equals 0 and theta at d equals 0. So we can totally do this numerically, okay? So here is a numerical solution, okay? So this is a numerical solution for varying values of the ratio d over psi, okay? And so here in this picture, I have d over psi equals numbers like 3.2, 3.3, 3.4, and then going up to big numbers like 10 and 20, okay? So the plots down here are numbers where d is relatively small or psi is relatively big. Here are numbers where d is big or psi is small. Okay. So the plots like these are like my first guess. Okay, that's pretty good. The plots like this, these are plots where the director rotates a little bit and then it has to rotate back. Okay. So there's only a little bit of variation in the director. And then if the ratio d over psi is too small, then you just stay at 0. So that here, this is d over psi less than or equal to pi. Pi is a special critical value for this ratio. If the ratio is less than pi, then the director just stays in the z direction in spite of the magnetic field. Okay. One way to characterize the plots here would be to say, how big is theta in the middle? Right? How big is theta right here, halfway between the two walls? Okay. So here, theta between the two walls is 0. Here it's not 0. And eventually it gets up to a maximum value of pi over 2, or down to negative pi over 2. So here's a plot of that. This is theta in the middle as a function of this ratio d over psi. And what we can see is that the plot shows 0. There's no deformation up until we get to this ratio of pi. beyond that ratio, we can go up or down. So this is a symmetry breaking transition. It is a transition where we go from a state where the y and negative y are equivalent to each other to tipping one way or the other. And look, it looks sort of like a square root law here, doesn't it? Right? It looks like the theta in the middle is 0, and then it increases as plus or minus the square root of the field minus the critical field. So right about there, theta in the middle is proportional to plus or minus the square root of h minus the critical value of h, right? Or equivalently, plus or minus the square root of d over psi minus pi. So this is a lot like the other things that we've seen in this semester for symmetry breaking transitions, like the Ising model, right? That this square root behavior is very common. Right? Or it's like the homework problem that I assigned you with the arch, right? Remember, with the arch, and there's a mass at the top of the arch, and at some critical temperature, the mass will fall down, and it falls down to one side, or it falls down to the other side. Right? So in that problem with the arch, we have a competition between entropy holds the thing up, the entropy of the ideal gas holds the mass up, versus the gravity, which tends to pull it down. Here, it's the same thing, but it's not entropy versus gravity, it's magnetic field versus elasticity. But it's the same sort of idea, and it gives the same sort of result for the symmetry breaking transition. Okay, I've gone over time here. I'm sorry about that. I need to stop talking. So this is, a classic example of a liquid crystal physics problem where we're calculating the director field. And I wanted to present one kind of example of that for you. So this is the sort of variational calculus problem that can come out of minimizing the Frank free energy. Okay, I will stop here and I'll be glad to answer questions about this or anything else. Thank you.
Yeah, I have it should be pretty quick. Going all the way back to when you were first putting together, would you be willing to go back in the slides all the way back to when you were first putting together the first term in the Frank free energy?
Let's see. Would that be this one?
Yes. For the second to last line, can you just quickly explain why that is equal to d theta dx in case I'm missing something?
Oh, just with the trig identity. That here, this is factoring out its.
Oh, I'm sorry. I'm looking at it. I'm being stupid. Okay, yeah, that's just
theta dx theta,
squared
right? And this sine squared plus cosine squared is 1.
Is 1. Yeah. Okay. I wasn't looking at it closely enough.
Yep,
Thank you.
Yep, that's all.